Hello everyone and welcome to a new problem of this chapter, which is the problem number of distinct values. This is a super interesting problem because it has multiple solutions, but two of them will perfectly show us how we can apply what we've learned so far, and the third one will be for a next chapter. So let's see the statement. Given an array of integers, count how many distinct values exist in the array. And let's take an example. The example here is this array nums, which has 3, 6, 9 elements. And as you can see, the integers could be either positive or negative. The array is like the order of the elements is random. And for this example, we just need to return 6, which is the number of distinct values. And why is that? Because the distinct values in the array are 1, 5, -3, -4, 2, and 7. For example, you can see this value 1, which appears exactly twice in the array, here and here, right? It's not important if the value appears more than once, but we have to make sure to count it only one time. So let's come up with a brute force approach for this problem at start. If we think about the simplest case possible, this is the case in which this array nums has only distinct values, right? So no value appears more than once. For example, 1, 2, 3, 4, right? And the answer is pretty obvious. It is the length of the array. But when that's not the case, that means that there will be some values or some elements from this array which we shouldn't count. For example, let's say we take a look at the first value in the array, which is 1. All right, we can count it. No problem. 5. We can count it. No problem. -3, let's count it, no problem. But if we also count this one here, that's not good. And why is that? Because we have already taken into consideration the value 1. So one way of looking about this problem is that for each distinct value, we just have to make sure that only on its first appearance in the array, we are going to increase our solution. On all the other appearances, we do nothing. So for example here, because this is the second appearance of 1, we don't increase our solution. The solution stays 3. -4, first appearance, solution is 4. 2, first appearance, solution is 5. -4, second appearance here, we're not going to take into account. 7, first appearance, yes, and the second 7, because it's on the second appearance, we don't take it into account for our solution. So as you can see, we have incremented our solution only on a couple of elements from the array. Now we need to find a smart way to check if some element has already been encountered in the past. And this is all, right? And let's think about what I've done here in this example and try to convert my thoughts into code. So, I've started off, in my mind, with the solution as being equal to 0, right? Before even going through the array. Then, I started looking at the elements one by one, from the first one to the last one. And for the first element, obviously, I don't have any elements on its left, so it's impossible to have already encountered the value, right? So what I do is I increase the solution. Then I am at the second element, right? What have I done here? I looked on its left, and what I see is only the first element, which is 1, which is different than the current element. So obviously I haven't found this value before, and the solution becomes 2. I go at the third element, and again, I know it has 2 elements on its left. I take a look at them, 1 and 5, and because both of them are different than -3, I increase the solution and it became 3. I go to the next one, right, the fourth one, and again, I take a look at all the elements on its left, 1, 5, -3, and because I found an element on its left which is equal to it, that means that I've already encountered that value. which means that I've already incremented the solution and basically taking the value into account, so I won't do it again. And I just jump to the next one. -4. Again, take a look on its left, 1, 5, -3, 1. I wasn't able to find the element equal to it, so I can safely increment the solution. Now it became 4. Next element, which is 2. Take a look at all the elements at its left. No 2. This means that I can increment the solution and it becomes 5. -4. Take a look at the elements. I find the -4, so I do nothing. 7. Take a look at all the 7 elements at its left. No 7. I can safely increment it. And of course, the last element, which was 7. Take a look at all of them. Already found the 7. So I've already taken the value into account. So the solution stays 6. And then, of course, I finish the array. And this is it. So all we have to do is, first of all, go through each element on the array from left to right. And then for each element, go through each of the elements on its left from left to right and just check if all of them are different than my -4. If I find one that is equal to the current value, then I can safely stop and say that this value was already encountered. So of course, for going through every value in this array, this is a repetitive thing, right? So we obviously need a loop. We can have a for loop to iterate through the elements. And for checking if some value was encountered before, again, I'm gonna have to loop through the elements on its left. This is also a repetitive thing. So I'm gonna need a second for loop, which is inside this one, to go through all the elements until, of course, I finish them or I found one which is equal to my value. So let's take a look at the code. Awesome. And here is the algorithm. So, as I've said, I'm going to start with a variable solution, which is initially 0. And then I'm going to iterate through every element of this array nums. Now, in order for me to do that, I have used an index, right? The index I, to go through every position from 0 to n-1, where n is the length of the array, right? Now, for the element nums of I, all I have to do is check if there is another element on its left with the same value. So I go through every element on its left, and those are the elements starting from position 0 and ending at the position i-1. And if I encounter an element, nums of j, which is equal to nums of I stop the for loop, right? So this is pseudocode, and this is why I've written stop, but in most languages it's break. I will get out of this for loop in one of two scenarios. Either I get out of the for loop naturally when j is getting increased and becomes greater than i-1, e.g. its value becomes I. So either when j becomes I, and we've gone through all the values on its left and found none of them to be equal to nums of I, or the second scenario is this one, when we exit the loop here with the stop or the break, which means that we have found an element on the left of nums of I with the same value. This is exactly why I check this, if j equals I after getting out of the for loop. Because if j equals I, this means that we've gotten out of the for loop naturally. So we've checked all the values on its left, on the left of nums of I, and found none equal. Because if we did, then we have stopped here with a value of j between 0 and i-1, right? So this is super important. Let me give you an example. Let's say I was checking -4, right? So the current I was here, 0, 1, 2, 3, 4. The index was 4. And I want for this element -4 to check if I have some other element on its left equal to him. And what I do? I use the pointer j and try each and every one of them. Initially j equals 0, They are not equal, so we do nothing and we move to the next j. J equals 1. They are not equal. We do nothing. Go to the next j. They are not equal. Go to the next j. They are not equal. Go to the next j. And here eventually j also becomes equal to 4. And when we try to get inside one more time in this for loop, we see that, oh, j is not between 0 and I minus 1 anymore. So we get out of the loop. Here we check j equals I. Yes, it does. Aha, this means that I've gone through all the elements on its left and never executed this break loop, right? This break condition. So if this happens, I'm gonna increase my solution by 1 because obviously this is the first time I encounter this value. And in this way, we make sure that on the other times, and let's also have an example with that, the future times I encounter a value of minus 4. So for example here, if I equals 0, 1, 2, 3, 4, 5, 6, right? In this example, I do the same thing. J0, they are different, I do nothing. J0, different, I do nothing. J1, do nothing. J2, do nothing. J3, not equal, do nothing. J4, and here is the first time that I actually enter this if statement. So I stop. So no matter what happens next, I'm gonna get out of the for loop and I'm gonna be here at this stage. And I see that j is not equal to I. Aha, so j points to an element equal to nums of I. Yes. So I won't execute it, meaning that I won't increase the solution and move on, right? So this is one way of solving this problem. Now the question is, what would be the time complexity of this algorithm? Well, that's a good question. Again, when we look at it, we see that we have our first for loop, right? Our second for loop, the inner one, and then an if statement and a return, right? So let's first take a look at the inner for loop. Obviously, the number of iterations we do in this for loop is not constant. It could be more for some elements, it could be less for other ones, right? For example, for this minus 4, we've done 1, 2, 3, 4, and then exited. For this 7, we are gonna do a lot of them until we hit this 7. It is not constant, but that's not important because it is not constant. In this type of situations, as you know, we always have to think about the worst case scenario. So let's think about for this for loop. What's the worst that can happen here? Well, obviously, the worst case is that we never execute this stop and we do each and every iteration we're supposed to do. We can't do more than I iterations at this for, right? So let's suppose this always happens. And for each I from 0 to n minus 1, when we enter this for loop, we always make I iterations. Let's just suppose that. It's pretty simple to think about a scenario where this happened, and that scenario would be an array nums, where in fact all the elements are distinct, right? Let's take 1, 2, 3, 4, 5 as an example. Think about it. Obviously, when I equals 0, yeah, we have no elements on its left, so we do 0 operations, right? That's a 0. Plus, when I equals 1, so the second time we enter the for loop, we are here. And what happens? Well, yeah, we are gonna iterate through each and every element on its left. Only one of them. Plus, next time, when I equals 2. So here, because as you can see, all the elements are distinct, we are in fact going to iterate through each and every one of them, because we never stop, right? So again, I have 2 operations. For this element, all of them are distinct. I have to make like 3 iterations because I never find something equal. to break out of the loop earlier, I have other 3 operations, and for this one, I have, of course, other 4 operations. So as you can see, it's pretty easy to notice that the worst case scenario is an array with only distinct elements. And the number of operations we do in that scenario is, for each value of I in the inner loop. So it's this sum, 1, 0, plus 1, plus 2, plus 3, plus 4. That's in this example, because the length of the array is 5. But on a more general example, let me clean this up. On a more general example, so for an array nums of n elements, let's denote the number of elements with n, we will have 0, plus 1, plus 2, plus dot, 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 plus n minus 1. And this is, as we know, the Gauss sum, n crossed n minus 1 divided by 2, right? N crossed n minus 1 divided by 2. Because we don't take constants into account, the conclusion is that this algorithm actually has a time complexity of big O of n squared. And that's not good enough, unfortunately, because obviously if you have an array of 100,000 elements, big O of n squared is a lot. So we are going to come up with a faster approach. So the problem with the previous approach was that for each element, we had to look at all the elements at its left to see if there is one equal to it, right? Because we couldn't know where that element might be. So for example, for this minus 4, we'll have to check each and every one of them until we find this one. For 7, each and every one on its left until we find this 7. For 1, fortunately, only for this example, we had to check only 1 because it's here on the first position, right? On index number 0. So the problem is that if that element, if our current element had at least one other element on its left equal to it, we don't know where that element might be. So we need to check each and every one of them. But if there was a way to tell exactly where that element might be if it existed, that would be way easier, wouldn't it? If let's say that for this 7, for this last element, I knew for sure that if there was another 7, it would be on its left. Awesome, I just have to look at the element on its left and just compare these two. But that doesn't happen for every element in this array, right? For example, for this minus 4, I look at the element on its left, it's 2, and I can't say that, alright, there's surely not another minus 4 on its left, because the element is actually here. If we found a way to rearrange these numbers such that when I want to check if an element has been found before, I just have to look at the one on its left, I definitely had a linear approach. And we can do that. Is there an order of these elements where we can definitely apply our strategy and be right about it? It is. And that order is having the elements sorted increasingly. Let's take a look at how this array will look after we sort it. The sorted array will look like this. The beautiful thing here is that when you have an array sorted, you will have the equal elements one after another. Minus 4, minus 4, minus 3 alone, 1 and 1, 2 alone, 5 alone, and 7, 7 alone, right? So, what happens here is that when we go through each element in this array and want to check if this is the first time we've encountered it, we just have to compare it to the previous one. For example, minus 4 obviously doesn't have an element on its left, so we can just increase our solution. So the solution was 0 and now it's 1, right? Then, next element, minus 4. Compare it to the one on its left. They are equal. This means, of course, that we won't take it into the solution anymore. the next element, minus 3. What's the element on its left? Minus 4. They are different. More exactly, the previous element would be less than the current one if they are different, right? So let's think about it. If the previous element is less than our current one, and we know the array is sorted, this means that every element on its left will also be less than our current element, right? Because they couldn't be greater. So we can say for sure, after only checking this, that minus 3 has been encountered for the first time. Next element is 1. Again, on its left, it's minus 3, which is less than 1. So of course, every other element on its left is going to be less than 1. Increase the solution. Next one, 1. With the previous element, they are equal, so obviously it couldn't have been the first occurrence. Next element, 2. Previous one, it's 1. 1 is less than 2. So every other element on its left is also less than 2. So what you're going to do here, increase the solution, of course. 5, greater than the previous one, also increase the solution. 7, greater than the previous one, also increase the solution. And 7 equals 7, and we do nothing. And we found out that our solution in the end is 6, which is indeed the right one. So see the beauty of sorting arrays. Just having the elements in the right order could sometimes make our life way easier. Now let's take a look at the code. Alright, and here is the algorithm. So, first of all, 2 mentions. The first one is that I've purposely made a mistake, and you're supposed to find it, or we will find it together. If you can't, that's cool. And the second one is that I've just written here sort nums, because there are a lot of ways to sort the array, and that's not the purpose of the lesson, right? So first of all, we sort the array nums, and then we start off with the solution equals 0, and then all we need to do is go through each element in the array. So I'm taking the index from 0 to n minus 1, where n is the length, and just check if that element is different than the previous one. And if they are different, just increase the solution, which will be returned in the end. And this is it. Only that. Now, about that mistake, you might have noticed it, but I want you to be very careful when going with indices on the left or on the right. In this example, be very careful when you try to access elements in the array, because this I starts from 0. So on the first iteration, my I becomes 0, and nums of I minus 1 becomes nums of minus 1, which obviously doesn't exist, right? So be very careful to never go out of the array's bounds, because that's going to be a runtime error and definitely a red flag for every interviewer, right? So in this example, all I had to do is to make sure this won't happen. I have to make sure that I minus 1 is always greater than or equal to 0, which means that I is always greater than or equal to 1. So I can start from 1. This is cool. Now the problem is solved. But also, I'm not iterating through the first element, which is bad. But in fact, as we know, the first element is always on its first appearance, right? I couldn't have found it earlier because I have no elements on its left. So I can just initialize solve by 1 and then start from the second element and do the algorithm. Now let's think about the time complexity of the algorithm. As you can see, I'm initializing the variable by 1. That's constant. Then I'm entering this for loop, which has an if statement and an addition, right? The addition is constant. The if statement is again constant time. So all we need to ask ourselves is how many iterations does this for loop do? Well, it's pretty obviously, right? It's n minus 1. So we are doing n minus 1 iterations, and inside each of them we are having only constant operations. So don't worry about them. Well, that's okay. But don't be tempted to say that the complexity of the whole algorithm is linear, because it's not. Only this part Starting from solution equals 1 to return the solution is constant. And that's right. But don't forget that before this, we have to sort the array. And what's the time complexity of sorting an array of n elements, where the elements are integers? It's big O of n log n. Yes, there are some arrays for which you can sort it in linear time, using count sort or maybe radix sort, but this is not the case and not the point. The point is that when having all kind of values, negative, positive, could be large, sorting an array is big O of n log n, and then doing our algorithm is big O of n. So what I'm gonna do here, choose the big O of n or choose the big O of n log n? Of course, always the greater one. Big O of n log n will be the final time complexity of our algorithm. And that's it, guys. As you can see, we are not using any extra memory. Of course, a couple of variables, but they don't count. So we have big O of n log n, time complexity, and constant extra memory, which is great. There is a better solution for this, which we are going to see in our next lessons, which has linear time complexity, so big O of n, but with the expense that the memory complexity is also big O of n. It depends on interviewer. It depends, of course, on the real life scenario. Sometimes you'd like this one. Sometimes you are able to go with a little bit more memory just to make it faster. Enjoy coding, and as always, see you on the next one. Bye.